let's look at measures of the spread of data or variability in section 2.7. We're still talking about numerical descriptive statistics. These ones measure how spread out data values are from each other. So first of all, the range measures the spread that's between the extreme values. And it is based on just two of the data values in the data set. We take the maximum value or the max value, and we subtract the minimum value. So it's a quick way to get an idea of how spread out the data is, but it only relies on two of the data values in the entire data set. Other two measures of variability are variance and standard deviations, and these measure the spread of the data values within the extreme values. And specifically, they are based on the average distance away or deviation from the mean value. So I want to focus on this average distance away because that's something we can wrap our heads around. So we have a mean value of a data set, and now we want to find what's the average distance away each of those data values is from that mean value. Okay, so that's what we're getting at with this measure of variance and standard deviation. So we're going to actually derive a formula to find the standard deviation. Okay, here is some sample data, and it is giving us a sample of 5 car accident patients and the number of days that they spent in the hospital recovering. Okay, so here we're using some notation. We're using I as an index, so we have 5 sample values, and so our I ranges from 1 up to 5. And then the X sub I values are those 5 different data values. So 3 days, 4 days, 9, 7, and 2. And then I give a sum there of 25. All right, so the first thing we want to do is we want to calculate the mean number of days. So to do that, all right, we're going to take that sum of the X values and divide by the sample size. So we've got the 25 already calculated for us, and we're going to divide that by 5. So we get mean value of 5 days. Okay. Now, what we're trying to calculate is the average distance away from that mean of 5 days for each of the individual data values. So it would make sense then to find that distance away, or to find that deviation from the mean. So what we'll do is we will take each individual X value, so the X sub I, minus that sample mean that we just found. So if we go through and do that, we're going to take 3 minus 5, and we get a negative 2, 4 minus 5, we get a negative 1, 9 minus 5, we get a positive 4, 7 minus 5, positive 2, 2 minus 5, we get a negative 3. All right, now if we're looking to find the average of these deviations that we just calculated, we're going to need to add them up, all right, and then divide by the total number. Okay, so we're just finding an average. We're finding a mean of these deviations. Okay, so let's first of all add those up. So what we're doing is we're taking the sum of the X sub i's minus X bar. And maybe you've already done this in your mind. If you add those up, what are we going to end up with? Well, we end up with 0. Okay, so that is kind of built into how we came up with X bar. If we go through and find these deviations and then we add them up, we're always going to end up with 0. All right, so if we want to get some kind of measure of this average of the deviation away, we have to do something to that deviation so that it doesn't have negative numbers and isn't going to cancel itself out. Okay, so let's go through our list of things here. So for each data value, we already have done this. We found this difference, and we want to make sure we're naming that as a deviation. Okay. And we found that the sum of those deviations is 0, and it's always going to be 0 for any sample data set. If we go through this process, it's going to end up being 0. Okay, so we want to figure out what's something we can do to that deviation so that we get rid of negative values. Well, there's a couple of options. We could take absolute value, and we could square. Well, it turns out squaring is the option that we want to go with. It works a little bit better mathematically to do that. So if we go through and take each of those deviations and square it, whenever we square, we get rid of the negative. So negative 2 squared, we get 4. Negative 1 squared, 1. 4 squared, 16. 2 squared, we get 4. Negative 3 squared, we get 9. All right, now if we add that column up, and I'm not going to write that out, but if we add that up, that total is 34. All right, so we got something other than 0. Okay, so let's go down in our step-by-step here. So we added up the squared deviations, and we got 34. So let's just make sure we're calling those what they are, the squared deviations. Okay, now, so we've got the sum of these squared deviations. Now, if we go back to the idea that we're coming up with an average, right, we want to keep coming back to that, right? We want to add something up and then divide by how many there are. So it would seem like we would want to divide by 5, the sample size. But it is actually, it turns out that we're wanting to divide by the sample size minus 1. So we want to divide by 1 less than the sample size, which in this case is 4. This is going to give us a better measure of that overall deviation. Okay, so if we do that division by 4, this gives us a measure of variance. So variance, and I'm going to abbreviate with VAR here, equals, just to kind of get us caught up to speed with where we're at, is if we add up those squared deviations and divide that by the sample size minus 1, that's our variation, or I'm sorry, that's our variance. So in our case, we found that the sum of those square deviations was 34. We divide by n minus 1, we're dividing by 4, and that gives us a variance of 8.5. Okay, so we're starting to get at that average deviation away from the mean. We squared those deviations though, so that means we have taken whatever our unit is, in this case days, and we've squared it. So it's like we have something that's days squared, which we want to get it back to days. We want to get it in the same units or the same label as what our original data was. So to do that, we have to undo that squaring that we did. So we're going to take the square root of the variance to get the standard deviation. All right, so standard deviation, I'm going to just abbreviate that with SD then, is when we take the square root of the sum of the squared deviations over n minus 1. So in our case, that is, we take the square root of 8.5, that's the variance that we found, and it's equal to 2.91, and then that continues, and if we round to 1 decimal place, we have approximately 2.9. And because now we have taken the square root, we can put the same label on that value as our original data values. Okay, so what that's telling us is that the average distance away from the mean of 5 days for our 5 patients, or 5 car accident patients, is 2.9 days. So that gives us a derivation of this standard deviation and the variance. So let's just formalize that with some notation and the formulas. Okay, so we're going to start off with just focusing on the sample here. So for sample variance, we use S squared to stand for sample variance. And we already know what that formula is. All right, it's that sum of the squared deviations. And you'll notice, because we're talking about a sample, the mean value that we are subtracting is x bar, the sample mean. And then we divide by n minus 1, the sample size. Okay, so the standard deviation then is going to be denoted with S, and that is just simply the square root of the sample variance. So the square root of S squared. And then we just have some reminders there. Where we're looking at is the sample values x1 up through xn. N is the sample size, x bar is the sample mean. And we want to remember that S squared, and x bar are sample statistics. So they are based on sample values. They're based on values that come from a sample, from a population. Okay, if we want to now address the population variance and standard deviation, just like the population mean, that parameter, we typically don't know population variance or standard deviation. Okay, but if we want to formalize notation and a formula, we'll do that here. So variance, we use Greek letter sigma squared, and then that's going to be the sum of these, again, squared differences from population values minus, now instead of using x bar, we're going to use population mean mu. And then we divide that by the number in the population. And we are not subtracting 1 from this. And then standard deviation is going to be the square root of that. So we symbolize that with sigma. And that's just simply the square root of the variance. So the square root of sigma squared. Okay, so we've kind of added to our list of population parameters. So we had mu, population mean, and now we have population variance, sigma squared, and population standard deviation, sigma. So I'm going to just give us a reminder here of how to say this strange Greek symbol, and that is sigma. And when we hear that word, see that symbol, we want to think population standard deviation. Let's run through some practice, look at 2 samples of size 4, and find the descriptive statistics for each of these. So we'll start off with mean. We take our column of x values, our column of sample values, and add those up. All right, -1 plus -3, we get a -4. Add 4, we get 0. And then add 8 to that, we get 8. All right, so if we find x bar, that's going to be that sum of the x's over our sample size of 4. So that's 8 over 4. We get x bar is equal to 2. All right, now let's look at median. To get median, we want to make sure we're looking at the data values in ascending order. Okay, so I'm going to write that up above the table here. So -3 is our smallest value, and then -1, and then 4, and then 8. So we have an even number. So we're going to take the average of those middle two values. So our median is going to be -1 plus 4, which is 3 divided by 2. So our median value is 1.5. Let's look at range. That's where we take the maximum value and subtract the minimum value. So our max value is 8, minimum value is -3. So we got 8 minus a -3, so the negatives become a positive, so we get 8 plus 3, and our range is 11. Now we want to look at variance. Okay, so I have a column there that's going to help us calculate variance. So the first thing we want to do is to find the sum of those squared deviations. So we're going to take our data values, subtract the mean, and then square it. So -1 minus 2, we get -3 squared, 9. And -3 minus 2 squared, we get -5. Squared, we get 25. 4 minus 2 squared. 2 squared, we get 4, and then 8 minus 2 squared. We get 6 squared, we get 36. Okay, now we want to add those squared deviations up. So summing that column, we get 74. So to find our sample variance, okay, we're going to take that total, 74, divide it by 1 less than the sample size. 74 divided by 3, we get 24 point repeating 6. Now we're using our calculator to do this. We want to leave that 24.6 repeating 6 on our calculator and before rounding it, and calculate then the standard deviation. So that way it'll be more precise. So our standard deviation is the square root 24 point repeating 6, which is 4.9 repeating 6. And now if we want to round that to 1 decimal place, we go out to that 6, that's going to bump that 9 up 1, which bumps the 4 up to a 5. So we get 5.0 for our standard deviation. Okay, for our next example, I would suggest you pause the video and then work this out and then come back and watch it and check your work. All right, so we'll start off with finding x bar, the mean. So we have to total up this column. So 2 plus 7, we get 9 plus 11, we get 20 plus 4, so we get the sum of the x values is 24. So take that 24, divide by the sample size of 4, and x bar is 6. And median, here we want to make sure we are looking at the data values in ascending order. So I'm going to write those up here at the top. 2 is our smallest value, then 4, 7, and 11. Again, we have got even numbers, so we're taking the average of the middle two values, 4 and 7. So we add the 4 and the 7, we get 11, divide that by 2, we get 5.5 for our median value. Okay, next measure we want to look at is the range. All right, it's the distance between the min and the max, so 11 minus 2, so we get range of 9. Okay, now let's look at variance. So for variance, we want to find those squared deviations. So we got, for the first one, 2 minus 6 squared, so we get a negative 4 squared, so we get 16. 7 minus 6 squared, so that's going to be 1 squared. We get 1. 11 minus 6 squared, so that's 5 squared, and you get 25. 4 minus 6 squared. Negative 2 squared, so we get 4. And then adding that column up, get 46. Okay, now we can calculate sample variance. We take 46, divide by n minus 1, divide that by 3, and that gives us 15 point repeating 3. All right, so there's our sample variance. Okay, so maybe you're picking up on the fact that sample variance is used mostly to get to standard deviation. So we want to leave it in that sort of unrounded form, and then just immediately on our calculator take the square root of that and then round for the standard deviation. So taking the square root, we get standard deviation equal to 3.91, and it continues out, and so if we round that, we get standard deviation equal to approximately 3.9. Okay, so I will say that a lot of times we are not calculating standard deviations manually, but it is important to understand what a standard deviation is and how you do get at it. So there will be times over the course of the semester we'll revisit this and you'll be asked to calculate a standard deviation manually. So hopefully these two examples will be something that you can come back to and refresh your memory. Here's a couple applications of the standard deviation. So first of all is something called a z-score, and the second is finding outliers. Z-scores are the number of standard deviations away a value is from the mean. Okay, so it gives us a number of standard deviations away for any data set. Okay, so what is a z-score? For a value that's from a sample, a z-score is going to be the sample value x minus the mean, and so if it's from a sample, that mean is x bar, divided by the standard deviation. So for the mean, a standard deviation, for a sample, the standard deviation is s. For a population, a z-score is whatever the population value is minus the mean, so we use population mean mu, divide by population standard deviation sigma. All right, so x is always a value from the sample or the population, and for reasons we're going to discover in later chapters, we always round a z-score to 2 decimal places. Okay, so let's see what the z-score does for us. We're going to look at this example. Compare the mile times of 3 students with respect to their class and to each other. So we have 3 students. Rachel's an elementary student, Kenji's in middle school, and Netta is a high school student. All 3 of them ran a mile in 8 minutes. And then I've got recorded the mean and standard deviation in minutes for each of those classes below. Okay, so now let's compare each of these 3 to their class. Okay, so Rachel ran 8 minutes. If we look at the elementary students, she ran faster than the mean. So we could say that Rachel is faster than average for her class. Okay, because 11 is greater than 8. All right, so her time was faster. All right, Kenji was also faster. Right, because that mean for his class was 9, and that's greater than his time of 8 minutes. Netta, however, ran slower because his time of 8 minutes is greater than that mean of 7. Okay, so we can do that just straight from the mile times and the mean. But what if we want to compare them to each other and compare who was faster than average, more faster than average or slower than average from their classmates? So to do that, we need to know standard deviations. Okay, so let's look at the standard deviation for, or let's look at the z-score for Rachel. Okay, so if her mile time is 8, so we take 8 minus the mean for her class of 11, divide by the standard deviation of 3, which equals a negative 3 over 3, so her z-score is negative 1. All right, if we look at Kenji, z-score is, we take his time of 8, minus the mean of 9, divide by standard deviation of 2, and we get negative 1 over 2, so we get negative 0.5. All right, I'm going to go back up here and make that z-score rounded to 2 decimal places. Okay, so we get negative 0.5 for Kenji, negative 1 for Rachel, and now let's look at Netta. So we get z equals time of 8 minus the mean of 7 divided by the standard deviation of 4. So we get a positive 1 over 4, so 0.25 would be the z-score. Okay, so compared to each other, Rachel ran the fastest because her z-score, first of all, it's negative, so that means her score or her mile time is less than the mean. All right, it's faster than the mean, and it is more standard deviations below the mean than Kenji. Kenji's also below the mean because we have a negative. All right, but negative 1 is further away from the mean. It's a larger number in magnitude than the negative 0.5. So we could say, we can conclude here that Rachel, compared to the others, ran the fastest. So I'm just going to sneak that in here. Okay, so her z-score indicates that the number of standard deviations below the mean is more than either of the others. Okay. Also notice that Rachel and Kenji were the ones that ran faster than the average, and they are the ones that have a negative z-score. Netta's time was above the average, all right? It was a number greater than the average, and so there's a positive z-score. All right, so that's just an observation that we want to make. A positive z-score indicates that the value x is above the mean or greater than the mean. And a negative z-score indicates that the value x is below or less than the mean. Okay, one more thing we want to do here. We want to go the other direction. So what if we have a z-score of 1.3 and we want to determine what mile time for a middle school runner that corresponds to. Okay, well this mile time, all right, is equal to x. Okay, or let's just say x is equal to the mile time, okay, because that's like the data value. So that's what we're looking for. And just a reminder, z-score is x minus the mean divided by the standard deviation. Okay, so in this case, what is unknown is that x, right? We know z, it's 1.3, and that's equal to what the x that we don't know minus the mean that we do know of 9 divided by standard deviation that we do know, that's 2. Okay, so we have a little bit of algebra to do. We want to solve for x. Okay, so we multiply both sides by 2. So 2 times that 1.3, all right, and then 2 times the right side is just going to cancel out. And so we get 2 times 1.3 equals x minus 9. So x is equal to 2 times 1.3 plus 9, or 2.6 plus 9, which is 11.6. And we can put a label on that of minutes. The other application of standard deviation is outliers. We already looked at outliers and we looked at quartiles. We had a way to determine if we have outliers. This is another method. So as a reminder, an outlier is a value that's unusually large or small relative to the other values in a data set. So using z-scores, we are going to consider a value an outlier if it's more than 2 standard deviations away. That would make it a rare event. So more than 2 standard deviations away. So standard deviations, abbreviate there, away from, and finish that off, the mean value. Okay, so first step is to find the z-score for a data value, and then if it is less than -2 or greater than +2, okay, that tells us it's more than 2 standard deviations away from a mean, and we're going to consider that an outlier. All right, so let's look at this example. Let's say we've got the sample number of goals scored by a soccer team in 9 games, and it has a sample mean of 3.6 goals and sample standard deviation of 4.2 goals. And so we look at those list of data values, 3, 1, 4, 2, 0, 14, 2, 5, and 1. And this 14 jumps out at us as a possible outlier in the data. Okay, so let's determine if it's an outlier. So first thing is we're going to find the z-score of that value. So we take that value, that's the data value, x, subtract the mean, 3.6 divide by 4.2. That gives us z-score of 2.476. And rounding to 2 decimal places, all right, we want to go out to that 6. That's going to bump that 7 up to an 8. So we get 2.48. Well, 2.48 is greater than 2. So 14 can be considered an outlier. Okay, we want to consider the reasons that we could get this value of 14 and then what to do with it. So if we recall the 3 reasons, first was value is observed or recorded incorrectly. Okay, so if we can determine that 14 was really supposed to be 4, and we can make that correction, then we want to go ahead and correct that if possible. But if we know that 14 is wrong, but we don't know the correct, then we just throw it out and don't include it. Okay, now what about if the value comes from a different population? Could be that 14 is actually a football score, an American football score. And if that's the case, then it's coming from a different population and we don't want to include it. All right, so exclude. And it would make more sense. 14 would probably not be an outlier for a football score. All right, the other option then is the value is correct, but represents a really rare possibility, a really rare event. In that case, we don't want to exclude the data value completely, but we can look at the data with the data value included and look at the data with the data value set aside as well and see what impact that outlier has on the data and the summary statistics that we have for it.